Hi, my name's Dan, and this video is one in a short series of videos I'm doing about the digital electronics that are needed to add binary numbers together, which is part of a much larger suite of things showing the creation of a simple CPU uh, in digital electronics. And in the description below, there'll be a roadmap of where we're going in terms of that. And also a link to the software that I'm using to simulate digital electronics, which is called Digital Works. And in this video, we're going to address the fact that in the previous video we missed something out. We created in the previous video a thing called a half adder, and what this does is it adds two binary digits together. It's doing it one bit at a time, and it gives you the sum and carry outputs. Um, excuse me. Some of you who watched that video may have spotted that there was a problem with this, which is that the circuit we created only works for the least significant bit because any other digits that we're using also need to have a carry in, because when you carry out from one column, that needs to be factored in into the next addition up as you move up the columns, as you do uh, long addition. You start at the right hand end, add together the two numbers in the right hand end column. Right underneath it, if you're doing it with the pen, you write underneath what the sum is, and also you make a note as to whether you're carrying. So the circuits that we've got, if we're going to actually add up binary numbers that are more than one digit long, we need to have a circuit that will also include this carry in. And thinking about what we need, therefore we've got three numbers that are going to be added together. So our sum needs to be um, the result of that, of these three numbers, but we've still got to carry out, and the carry out will need to be there if we've overflowed. So if our result is uh, larger than one, and the four possible uh, how many possible solutions are there with three numbers that you can add together? There could be zero, there could be one, there could be two, which is binary one, zero, or there could be three, which is binary one, one. So our sum and our carry out need to take that into account. There is a standard solution. So for once, I'm not going to go to the truth tables and work out exactly what gates we need to do this. In fact, I'm just going to short circuit us to this standard solution. So I'm just going to show you what is done to solve this problem. And this is the universally used solution for this. And then once I've done it, I will demonstrate that it works and it does exactly what we want. Um, and the reason for this is twofold. Firstly, that because there is a standard solution, and I want to show you that. And secondly, because there would be other solutions as well, but and I don't want to get bogged down in kind of talking about the different possible solutions. So I'm going to go to Digital Works, which is the software that I'm using for simulating our digital hardware. And I've already got a half adder macro that I created, which I created in the last video. So I'm going to include one of those. In fact, I'm going to put two in. And this is the reality of why that circuit was called a half adder um, is because actually to do proper adding, which includes the carry-in, we use two of them. And most of the circuit that we need is these two half adders, and this is then called the full adder. So we're going to put in the A and B inputs, which we're going to need. We're also going to want a carry in input, which I'm going to put here. And we're going to need tags for, we need a sum output and we need a carry out output. And I'm kind of putting those vaguely somewhere where I'm going to need them. So what I'm going to do is let's label these first so that we know what we're doing. So that's going to be A. Let's have another one as B. And It's quite convenient that we've got A and B and then carry, which is a C. But this is C in, and we're going to also have sum and C out. So that's the thing that's taken through to the next column. All right. So how do we wire this up? Well, A and B can go to one of the adders. And then what we're going to do is we're going to take the sum of that result and feed it into the second half adder and take the C in and add that in. And if you think about that, when you're adding three numbers together, so you're adding in decimal 10, 7, and 8, mentally you might go through the process of adding 10 and 7 first, which gives you 17, and then adding 8, which gives you 25. And in fact, electronically, that's what we're doing here. We're adding A and B together first, and then we're adding in the C in. And the sum that we want is the sum of all three of those. So we're going to take that to the sum. The carry out is a slightly more complicated thing because we want this to be true if if two of A, B, and C are uh, are one, and in fact, if all three of them are one. And the way to achieve this is to actually take the two carry-outs from both of these half adders and just OR them together. So actually, if it's either of these additions overflows, then we want our carry-out. And just going to plug that across to there. Okay, so we've got two half adders. We've got the C in, we've got our sum out, and we've got our C out. And basically, to create this, we've put the two half adders together so that we're adding all three elements that are coming in, and we're taking the two carryouts, and if either of them are high or one, then our C out is going to be high. So I'm going to save this as a macro and then prove that it works. So file, if I haven't made a mistake. So save as, and we're going to call this adder full. In fact, we're going to call it adder 1 bit because this is a full adder, but it does 1 bit addition. Okay, so let's make a new circuit and drag our 1 bit adder in and stick on some inputs. Ha! So there is something that I haven't done, which is I haven't changed the template for our full adder. And in fact, it's still saying it's a half adder. We haven't got the pins that we need. So we need to go back into that our 1 bit adder because I forgot to do the template stuff. Okay. So the first thing that we're going to need to do is to edit that and call it 1 bit adder. 1 bit adder. And add another input, which is the carry in. Let's move these around a little bit. I'm actually just lining up that A and the B with those pins. I'm going to put another annotation in and call the C in. C in, reduce that down to 7 points. And we're going to just change carry out so that it says C out. Okay. Does that look right? Yes. Let's do the wiring up. So A input goes to A input. B to B. C in to C in. Sum out to sum out. C out to C out. Right, let's save that again and do what we were hoping to do before, which is to create a simple circuit to test this. So I'm going to delete that. In fact, let's do new circuit and get the 1-bit adder in. 3 inputs. 1, 2, 3. 2 outputs. Come on. LEDs, that's what I need. The second one. Quick bit of wiring up. I'm going to hit simulate and use the selection tool. So, current status, A is 0, B is 0, C in is 0. So let's check the sum first. In fact, yeah, let's not complicate things with that comment right now. I'll do that later. So if A is high, then we got 1. And if only B, then we've got 1. And if only C, these 3 should all react the same. So if we've got any 2 of them, the sum should be 0, but we get carry out. Let's try all the other combinations of 2. That's a combination of 2, sum 0, we've got carry out, and then that's our last combination. Yeah, come on. There we go. And then all 3 of them, we get the sum and the carry out. And you may have noticed actually that this is effectively, you've got 3 discrete lines coming in, and you're adding them together. And in fact, between the sum and the C out, this is actually effectively a 2-bit binary number coming out. The reverse, it should be C out is the most significant bit and sum's the least significant bit. But it is, I hope you can see, performing as we would want it to. So that's our 1-bit adder. And what are we going to do if we want to have binary numbers that are bigger than 1 bit? Well, the whole thing's been set up so that we can do this carrying process between the different bits, between the different columns. And so it's fairly obvious that we're going to be chaining several of these together to make a more than 1-bit adder. But that's the topic of the next video. So that's it from me for now.